Look at this LED. It's glowing brightly, but it isn't plugged into the wall, and there are no standard batteries hiding off camera. It is running entirely on apples and potatoes. Today, we are going to build a functioning multi-cell battery array using everyday produce, step by step. To do this yourself, grab a few pieces of fruit, pre-1982 copper pennies, galvanized zinc nails, alligator clips, a simple multimeter, and a low-voltage LED. You probably noticed the apples and potatoes earlier. We are also going to look at some university data showing exactly why the classic lemon battery you might have built in grade school actually uses the wrong fruit. By the end of this project, you'll convert the chemical reactions inside your groceries into a usable power source. Let's get started. Step 1 is preparing our workspace and fruit. Take your lemon, or apple, or potato, and roll it firmly on the table under your palm. You want to loosen up the juice inside, which acts as the electrolyte for our battery. Next, we need our positive electrode, or cathode. We are using a penny, but check the date carefully. You need a penny minted before 1982, because those contain the pure copper required. Push the penny into one side of the fruit, and a galvanized nail, which is coated in zinc, into the other. These two metals must remain separated inside the fruit. If they touch, the current bypasses our circuit entirely. Attach your multimeter leads to the coin and the nail. You should see a reading of about 0.9 volts. Here is what is happening. The fruit's acid reacts with the zinc nail. This dissolves the zinc, stripping away negatively charged electrons, leaving them stranded. Copper pulls electrons harder than zinc, so those electrons travel up the wire and down into the penny. That movement is an electric current. We are simply providing a path for electrons to escape a dissolving metal and reach a more stable one. This chart compares the power output of a lemon, a potato, and an apple. You can see the apple and potato distinctly outperforming the lemon. Tests at the University of Arkansas and elsewhere show that while acidity creates the ions, the dense cell walls and internal resistance of a lemon slow the current down. The physical structure of the fruit limits the power output just as much as the pH. Regardless of which fruit you use, we have a math problem. A standard LED needs around 1.5 to 2.0 volts to light up, and our single fruit cell is only producing 0.9 volts. Wiring fruits parallel, copper to copper and zinc to zinc, increases capacity, but voltage remains 0.9. To increase voltage, we use a series circuit. Alternating connections from zinc to copper stacks the electrical pressure. 3 fruits in a row now compound to well over 2.0 volts. Take your alligator clips and link 3 or 4 prepared fruits together in this alternating series pattern. You will end up with 1 free copper penny at one end and 1 free zinc nail at the other. By organizing the path the electrons take, we scale up a tiny chemical reaction into a functional power source capable of doing real work. Now grab your LED. A quick warning, do not test this bulb by touching it to a standard commercial battery like a AA. The high current will instantly destroy it. Our fruit array is gentle enough to work with safely. LEDs operate on polarity. They act like one-way valves for electricity, meaning the current can only flow through them in a single direction. Look closely at the metal legs on the bulb. The longer leg is always the positive terminal, and the shorter leg is the negative terminal. Take the alligator clip attached to the final copper penny in your array, that is your positive charge, and clip it onto the longer leg. Then, take the clip attached to the final zinc nail and connect it to the shorter negative leg to complete the circuit. Check your bulb. You might need to dim the room lights to see it clearly, but you should now have a steady glow powered entirely by your produce. Matching the physical flow of electrons to the correct hardware terminals is what turns a pile of raw materials into a working electronic device. Excellent work! You've successfully engineered your own biological power plant. We used the natural chemical reaction between copper, zinc, and acid to pull electrons from one metal and push them along a wire to the other. And when a single piece of fruit couldn't provide enough push, we bypassed its internal resistance by linking several together in a series to stack the voltage. Now it is your turn to experiment. Try building an array out of a strawberry, a slice of watermelon, or even a glass of soda. Test them out and post your highest voltage scores in the comments below. Proving a scientific principle doesn't require a pristine lab. It just takes a multimeter, a few household items, and the willingness to test a theory for yourself.